This is a collaborative project I'm working on with Rick Davis of our department, and and also Dr. Mason at RedMag. The goal of this project is really using so-called single particle tracking. This is based on laser-induced fluorescence microscopy to look at really the dynamic process of nanoparticle uptake and the intracellular transport. And single particle tracking offers very high temporal and spatial resolution. I will talk more about it, close to the end of this report. But then that's going to reveal important information about how the nanomedicine works inside the cell. And we are really hoping that the knowledge obtained will help design nanomedicine. And the specific type of nanomedicine we focus on is really using it against the intracellular bacteria. That's work, Dr. Mason has been working for years, such as Salmonella and Listeria. And in that particular case, certainly the intracellular transport of the nanoparticle would be particularly relevant to its efficacy. And the critical questions, I think, the technology will enable us to answer is that, first, for example, how is the physical chemical property of the nanoparticles, such as simple things like size or surface chemistry, affects its intracellular transport. And then, in turn, how does that transport affect its efficacy? And then the other thing is, because nanomedicine is supposed to be a carrier to get the drug into the cells, then how does the drug release from the nanomedicine platform occur? So these kind of answers can be obtained using single particle tracking. I'm just talking about the progress we made recently enabled by the seed grant. Dr. Rick Davis' group has been working very efficiently on making a fluorescent nanomedicine system with encapsulated drug. I guess in this case we use a fluorophore to replace the drug. Therefore, we will be able to look at the fluorescence change during the transport of the particle inside the cell, and then we would that's a mimic of the release of the real drug. So that's going to be important for such investigation. And Rick is using this PDLLA PEO diblock copolymer system, and we basically encapsulate a fluorophore in such a nanoparticle system. I guess, correct me if I'm wrong, Rick. My understanding is there is no covalent bonding between the fluorophore and the particle, but it's mostly based on hydrophobic interaction. We chose to start with the simplest fluorophore FIPC, very low cost, and it's reasonably hydrophobic, dissolvable in methanol. And so we measured the UV with absorption spectrum of the dye, and we used that to really to quantify later on the encapsulation or the incorporation of the dye into the particle. The fabrication is conducted using this precipitation procedure. I think Rick and Judy have been working on this for years, so it's very well established. And then we ended up with particle size roughly 71 nanometer. And if you put it in the annexed water, you may see a slight change in the size. And then we were measuring how many dye we successfully loaded in the nanoparticle system. I guess it's a little hard to read here. We basically look at the UV spectroscopy. We took the spectroscopy of the dye, and then we now can take the spectroscopy of the nanoparticle fabricated. Then using this calibration curve, we can quantify how much dye you have in the nanoparticle. And I believe it's 8% here. I cannot read it very well. So we were able to incorporate roughly 8% in the weight of the dye into the nanoparticle system. And we measured the fluorescence, emission spectrum. It's not that different from the dye by itself, after being incorporated into the nanoparticle system. And then you can see sort of it's, if it's excited, it lights up like a Christmas tree here. So we did look at the incorporation of such particle after production, certainly. They have no problem having these nanoparticles being uptake into the cells. So they are successfully labeled. Now we are ready to track their movement inside the cell. And the way we plan to do that is, now I want to talk a little bit more about single particle tracking. So the principle of doing that is that if you're using laser-induced fluorescence, you can see the fluorescent nanoparticles fairly clearly. You basically see these single dots in each frame you're taking. And then if you're using a Gaussian distribution to fit the image of the fluorescent particle, this dot, you can really localize the position of the nanoparticle within nanometers. And certainly that's also dependent on how fluorescently, how strong the fluorescence is. And if you're doing that so basically, if you just focus the laser in one part of the cell, and then you see a bunch of dots, they will be moving due to the thermal motion. And then some of the dots will be moving with certain direction due to the endocytosis. Then you will be able to recognize these nanoparticles. And then you sort of really register the localization of the quantum dots in each frame after taking the video, and then you will be able to track the trajectory of the dot, of the particle. So I guess I don't see that. Okay. So here you can see a image here. Stuck. Okay, for example, some of the dots, the movement is less interesting. It's mostly just a thermal motion. So for this particular dot, it sort of has this linear motion. We believe that's because we are using actually quantum dots, which is very photostable here. That's because of the really the movement of the quantum dots along the microtubule. You can see. Yeah. So that's the type of technology I was referring to by single particle tracking. So for the next, we'll certainly use that to look at the labeled nanoparticles, their transport inside of the cell, and certainly if we say we label the bacteria, for example, Salmonella with GIP, things like GIP, and then if we can look at both channels together, then we can see whether the quantum dots gets close to the bacteria, and how does that help, or whether that's important for the efficacy of such a drug in order to kill the bacteria. And then we can, in that way, we correlate the efficacy with the intracellular behavior. One problem, minor technical problem we are trying to overcome right now is photobleaching, because FITC is fairly unstable, but that was our basically first try. We knew that would happen, so we can adjust the lasers parameters, and alternatively we can do another dye. So that's basically where we are. And we did submit a proposal. This is a collaboration between me, Rick Davis, Dr. Nathan, and Dr. Judy Raffel. We submitted to USDA in February this year. There was a proposal I submitted a little bit earlier, last year, that was also using the single particle tracking technique, so which is really relevant to the seed grant. We have a paper coming out the end of last year. That's a collaboration with Dr. Mason, which is related to this. With that, I'll be happy to take any questions.
I think we'll save that for the break. We're
sure.
already into Carla's time, but nice job. Thank you.
I want to get out your way.
Carla has a video she's going to show us that she's going to link up.
Super. Thank you very much.